So this is joint work with Philip Isola and Alyosha Efros from UC Berkeley. Consider this iconic photograph of Yosemite Valley Bridge from Ansel Adams. How would it look like in color? Well, on the face of it, this problem is very under-constrained, as we're looking to produce a three-dimensional signal from a one-dimensional signal. However, you and I have seen many color photos, and we have no trouble doing this. We know that the sky is probably blue, the mountain is likely brown, and the vegetation is most definitely green. And so this problem clearly calls for the use of data, and we can use machine learning techniques to help solve the problem. Now formally, we're working in the LAB color space. So the L channel has the grayscale information and serves as the input to our system. We're looking to predict the AB channels or the color information, and we learn the mapping from L to AB using a CNN. We can then take the output predicted AB channels, concatenate them with the input, and hopefully get a plausible colorization of the input grayscale image. Now note that any color image can serve as a free supervisory signal for training this deep network. After all, any image can be broken up into its L and AB components. So perhaps by learning to color, we can actually achieve a deep representation that has some sort of higher level abstractions or perhaps even semantics. Now training this deep network may not be as straightforward as one may expect. For example, consider this example image. If we take the image, pass it through our system, here's our result. It looks plausible. Here's the ground truth image. Well, note that even though our prediction is red and the ground truth is blue, and these two are actually very far apart in AB space, we're perhaps just as happy with the red colorization as we are with the blue because it seems plausible. And what this indicates to us is that some sort of loss, which has some sort of unimodal assumption underneath, such as regression with L2, is going to be inadequate for this problem. Because in that case, if we have multiple modes, the L2 loss will simply average between them and give us a desaturated, unexciting result. As such, we recast the problem as one of multinomial classification. So we take the output space and divide it up into discrete bins of size 10. So here's an example predicted distribution from our system. The input image is on the upper left of the bird. Now each of these tiles corresponds to one of the output bins in our multinomial classification problem. And within each of the bins, the regions with high lightness value indicate high probability of being that color. Now if we zoom in here, you can see that the system has predicted the foreground object, the bird, to be blue, red, perhaps purple, and the background vegetation to be green, yellow, maybe a little brown. But this is not the end of the story. We also have to take into account the natural image statistics of natural images. So on the right here, we have a histogram showing the occurrences of all the colors within all the pixels of ImageNet, and this is shown on a log scale. And what you see is the majority of the pixels are concentrated in the middle of the gamut, where images or the colors are desaturated or bland. And so without taking this into account, with any uncertainty, the predictions that the network provides will tend to be desaturated or bland. As such, we add a class rebalancing term into our training objective. And this effectively resamples the rarer colors so that they're more represented than their actual representation within the training set. And it's the consequence of these two design decisions, going from regression to classification and then adding the class rebalancing term, that gives us results that are qualitatively more colorful than previous and concurrent approaches. Hence the name of our project, Colorful Image Colorization. So how does our system compare to previous work? Well, many previous techniques have focused on using a non-parametric framework. So in the non-parametric framework, a reference image is first obtained, and the colors from the reference image are then transferred over to the grayscale input image. Now this technique can actually work very well, but it can also fail to generalize. And also getting the reference image itself can be slow or require some user intervention. Now parametric techniques, some previous parametric techniques have also used L2 regression, both with hand-engineered features as well as deep networks. We're also not the first, of course, to cast the colorization problem as multinomial classification. There's actually some older work from Sharpia et al. From ECCV 2008, which proposed using a classification framework for the colorization problem, and this work actually inspired us. There's actually some concurrent work from Larson et al. That are going to appear in these proceedings, and they'll have a presentation tomorrow morning, so we highly encourage you to attend their talk as well. Okay, so how do we map from an input lightness image into an output color? Well, first we note that we've converted this problem into one where we predict a probability distribution for every pixel. And as such, we can draw on many of the insights and advances in the semantic segmentation literature to help solve our problem. So we start with a VGG network. This is actually trained from scratch, so it's just the architecture. We remove the FC layers. We add some additional spatial resolution in the bottleneck using outtrue or dilated convolutions. We add some additional convolutional layers on top and then map the features into a predicted distribution for every pixel. Now there's one final step, which is going from the predicted distribution into a single point estimate. To do this, we take an interpolation between the mean and the mode, and this allows us to keep the vibrancy of the output colors while maintaining some spatial consistency. Okay, so how do we do? Well, let's consider this input image of a boat. If we use an L2 regression loss, you see that the result looks just fine. And this is because the sky is blue and the vegetation is green, and there's very little uncertainty, so L2 serves us well. Our final system does just as well on this image as well. But let's consider the input image of this bird. Well, using L2 regression will give us sepia or desaturated result, whereas our technique will give us a bright blue colorization with a nice yellow belly. Now, how does the input actually look in ground truth? Well, you see that the bird is actually yellow. And even though the yellow ground truth bird and our blue prediction are far apart, we're happy with our results because it seems like a plausible colorization. Okay, of course, the problem is most definitely not solved. So there are failure cases that we've observed in our system. So one common failure case is that man-made objects can actually be one of many different colors. And our network at times has difficulty in choosing one to ultimately go with. And this can result in the output having some sort of tie-dye pattern. There are also some kind of curious biases that we fished out of the system. What we notice is that when the network sees a dog face, it actually expects the dog to have its mouth open and its tongue out. And even when this doesn't happen, the network goes ahead and hallucinates one for us anyways. Okay, so one of our contributions is to really carefully think about how to carefully evaluate the colorization problem. So previous papers have used metrics such as per pixel accuracy. And we evaluate these in our paper as well. But per pixel accuracy does not speak to the joint interaction between pixels as well as the overall perceptual quality that we're really shooting for. Now, no metric is perfect, so we propose a number of them that get at different aspects of this problem. Now, note that our problem is an example of an image synthesis problem. And actually, some of the approaches that we've proposed can be applied in those other image synthesis problems as well. We also evaluate the colorization of task itself in its ability to produce strong representations. Now, due to time constraints, we won't be able to discuss all these evaluations, so please come to our poster for additional details. To begin, we'll discuss a perceptual realism test that we ran using Amazon Mechanical Turkers to provide real human judgments as to how our system is doing. And we'll actually invite all of you to participate in a version of this test right now. Okay, so we're going to show you two images. One is going to be ground truth, and the other is going to be our fake image. And it's up to you to decide which one is fake. Okay? So if you're ready, we'll begin now. Image number 1 and image number 2. Now please clap if the left image is fake. Now please clap if the right image is fake. Okay, very good. So I think all of you were able to identify this very visible smudge and the lack of spatial consistency on the truck, which served as a dead giveaway on an otherwise perhaps good colorization. Let's try a case that perhaps we perform a little better in. Image number 1 and image number 2. Clap if the left is fake. Clap if the right is fake. Okay, about 50-50. So in this case, we predicted a color that was actually very close to the ground truth. In these cases, we'll fool participants at about a 50% rate. Let's try one final test. Image number 1 and image number 2. Clap if the left is fake. And clap if the right is fake. Okay, so what happened in this case? Well, the ground truth image was of a blue chameleon, but our network actually learned that chameleons typically appear green. And so in these kind of outlier cases, our network can actually make predictions that are more prototypical than perhaps the input image, and we can actually get fooling rates above 50% in these cases. There's some other examples of this behavior that we've seen as well. So this input image is actually from a Reddit user, and what we find is that if you take your dog out for a color run, you can actually use our system to clean them up. And if you take a colorfully tiled Yoda, we can actually make him green again. And so these images were actually processed by the Reddit Colorize bot, which a third party or another user wrote and is using our system in the back end. Okay, so how do we fare quantitatively on this metric? Well, if we were to produce perfect ground truth colorizations, we would achieve 50%, almost by definition. If we add the colors from a random image, we get 13%. With L2 regression, we get 21. With classification, we get 24. And our full system gets 32. The system proposed by Larson et al., which is concurrent work, which uses a multinomial classification framework with a different architecture, gets 27. And this suggests to us that our design decisions, going to classification and using a class rebalancing term, gave us colorizations that were more plausible as judged by real human users. So let's try to get some insight into how our network is actually doing this. So if we try to color these two equiluminant vegetables, our system does okay. Now, how about this Macbeth chart, which is never seen in training? Well, it fails. And this indicates to us that instead of using some sort of low-level hack or cue, such as perhaps chromatic aberration, the network actually is learning perhaps how to recognize the objects themselves. Now, normally to get a representation that recognizes objects, we can directly train for the task using object labels, for example, in an ImageNet classification framework. And this is in a supervised setting. Now, colorization, on the other hand, is an example of unsupervised, sometimes referred to as self-supervised learning. And in this paradigm, we take the input, split into two pieces, and then ask the network to predict a held-out piece from the remaining piece. Now, there's been a flurry of activity kind of in this paradigm, especially in the past year, using cues such as co-occurrence, context, ego motion, and video. And actually, yesterday, we saw an example of audio. And there's been other concurrent work in these proceedings, in this conference, that have extended some of these frameworks as well. Now, our network, or the colorization task, is somewhat similar to denoising autoencoders. So for denoising autoencoders, we take the input image, we add some random corruption, and ask the network to undo this random corruption. On the other hand, for our task, we add a systematic modification to the signal. That is, we drop out two of the channels and ask the network to predict those two channels from the remaining grayscale channel. And so we call this general framework cross-channel encoding. Okay, so how does our system do in comparison to others? Well, to help answer this, we retrained the network for the colorization task, but this time using an AlexNet framework. And we strip away everything that's specific to the colorization task itself, and we're left with a generic feed-forward feature extractor. So to begin, we'd like to qualitatively assess if any of the units may have some learned semantics. And to do this, we observe images which maximally activate certain units in the COM5 layer. So what we see is some units which correspond to stuff categories, such as sky, trees, and water, and others that correspond to more thing categories, such as faces, dog faces, and flowers. And note that the network was able to discover these units without the aid of labels. So this was done in an unsupervised regime. So we have some indications that the network is learning semantics. But how does the feature representation do when it's asked to transfer to other data sets and tasks? So to get at this quantitatively, we fine-tune the network on the tasks of classification, detection, and segmentation on the Pascal VOC dataset using some established frameworks from literature. So here on the y is equal to 0 line is the performance if we were to simply use a Gaussian initialization for our network. The performance that we're looking to match, or hopefully someday beat, is if we pre-train using ImageNet labels themselves. And on the y-axis here, we're going to plot the amount of ground we've made up between Gaussian initialization and a fully supervised pre-training. Now, one way to get features is to use an autoencoder, but autoencoders do not seem to actually get very semantic features. Now, if we use a stack k-means approach as implemented by Krahumbull et al., this will take us partway between Gaussian initialization and ImageNet labels. And here we've shown some previous self-supervision techniques using cues such as ego motion, in-painting, video, relative context. The method from Donahue et al. Is an adversarial feature learning framework. And here are our results. So note that other than the very strong performance of the Dorsch method on the detection task, using colorization, actually is very competitive and sometimes even state-of-the-art relative to previous self-supervision methods. And this was actually kind of a surprise to us because at the outset of our project, we were mostly focused on the graphics task of colorization. But do note that there is still a very large gap between all these self-supervision methods and pre-training with ImageNet labels. So there's still a lot of work to be done in learning semantic representations in an unsupervised way. Okay, so we've seen a bunch of examples of images, but those images started off as color images. How does our method actually work on legacy black and white photos? We show a few examples here. So this is a thylacine, which went extinct in 1936. So there are no color photos of it as far as we know. And so here's our result. Here's an amateur family photo taken in the 50s, and this is actually of my father and my great-grandfather. This is a professional photograph from Henri Cartier-Bresson. And finally, this is an iconic American photograph of migrant mother. Okay, so for some additional information, you can go online and see the demo. You can also test our system on Reddit. You can also look at our code or go to our website for full paper and visualizations and some user examples. And we'll actually play us out within a user example, a user video that was submitted to us while we take questions. Thank you for your attention.